Is that good?
It should be.
All right. There's only 2 participants, but it's the posterity that's important. Okay, let's move on. So, yes. Good. Now, and my pointer isn't working. Why isn't the pointer working? It's giving me a click. Oh.
Is there antenna?
The antenna's there. No, it was working fine until we did I don't want to have to sit here. It's good. We're good. We're good. Okay, so I want to begin by talking a bit in general terms about topology and fractionalization. And so what is fractionalization? It's this amazing discovery in condensed matter physics that we can have emergent excitations, and these emergent excitations, which some people call partons, are excitations which move in which describe the breakup of operators like charge or like spin in terms of constituent particles. Okay, and so, for example, we might have a magnet where the traditional excitations are spin-1 magnons, but when fractalization takes place, a spin flip creates pairs of particles, spin-ons or Majorana fermions. We might have a fractional quantum Hall system in which the addition of an electron creates triplets of anyons. Okay? And so this is the classic example of fractalization. It's the 1D Heisenberg antiferromagnet. And when you flip a this is not working on now. Okay, good. When you flip a not that either. Okay, when you flip a spin to create a magnon, it breaks up into 2 spin-1/2 domain walls or spin-ons. Okay? And so nowadays we have examples of such fractalization even taking place in models of 3-dimensional spin systems. And I'll tell you a little bit about this exactly solvable 3D Pauli spin liquid in which the spin breaks up into spin-ons which carry spin 1 and they move on a Fermi surface. So I'm not sure whether this is the right language, but we're using the word parton here as a kind of emergent quark. So let's talk about quarks for a second. So quarks, although they're confined, they leave their imprint through meson and baryon multiplets. None of us, perhaps we can see a quark in a quark jet, but at long distances, quarks are confined. Nevertheless, they influence the world we are in. They describe the multiplets of mesons and baryons that live in our world. And so, can there be an analog in condensed matter physics? So, in condensed matter physics, we might have the possibility of almost deconfined excitations manifesting as virtual resonances. And we're particularly, we're particularly interested in the possibility that fractionalization might modify the structure of phases, might lead to virtual resonances, and so that the analog of mesons in particle physics would be the phases of condensed matter physics. And so such new phases can manifest themselves as perhaps heavy fermion superconductors, Kondo insulators, and that's our interest in the fractionalization angle here. And the topology comes in because the deconfinement of excitations often involves topological phase transitions that don't actually have an order parameter, but can be studied using statistical mechanics methods such as the Boole algorithm. And so I'm going to try to draw these two ideas together in this talk. And if time permits, show you some work I've been doing with Anatoly Kuklov and an exaspheric, which provides perhaps some perspective on this situation. So all of this work has basically been kicked off because we have a new technology available to us as theorists. We have the technology of the Kitaev spin liquid. And the Kitaev spin liquid, curiously, could have been discovered by Jordan and Wigner years ago. It's just that they didn't realize that the method that they invented would actually extend beyond one dimension. So an example of this playground is the 1D Kitaev model, which is literally the XXYY chain. If you take the XXYY chain and you treat it with the Jordan-Wigner transformation, representing sigma x as a fermion with a string, then lo and behold, you can show that this model is describing a single chain of Majorana fermions. And what's really going on here is that the spin has actually broken up, according to the Kitaev picture, in terms of a single Majorana fermion that doesn't carry spin and a triplet of vector Majorana fermions which decouple as gauge fields. So in the case of this 1D example, what you actually find is that you have some leftover Majorana fermions sitting on the edge of the chain, which decouples, and you have this mobile band of A Majorana fermions running along the chain. So it's interesting then to ask what happens if you then take this and connect up side chains. Well, lo and behold, what happens is that these side Majorana fermions form gauge fields, green gauge fields. And what then happens is that you obtain a two-dimensional spin liquid described in terms of these Majorana fermions hopping between the chains through this gauge field described by the green fermions. And so this is a way you can reconstruct the approach of Kitaev using old-fashioned Jordan-Wigner transformations. And the reason it's rather nice is that you can see directly how fractionalization is working using an old-fashioned medium. Okay? And in fact, you can go further than this. One of the things you can do is you can construct any lattice with 3 bonds per side, and you can tile the plane with XX, YY, ZZ Ising couplings. And you can then solve that, if you like, using Jordan-Wigner methods, or if you prefer, using Kitaev's parton method. And the result of this, in this particular lattice, is that you get a Fermi surface of Majorana fermions propagating around. It's rather remarkable that the Jordan-Wigner transformation can be used on this curious little lattice, and you get mobile 3-dimensional excitations. Yes, Andre.
What sets their density of fermions, or in other words,
So in some sense, that's absolutely fascinating in this particular case. This has 4 sites per unit cell. Okay, so it has, if you like, 4 bands there, and this thing here is a particle. There isn't a sum rule on the size of the Fermi surface coming in here. Actually, you can change the parameters, and you can actually make this Fermi surface completely disappear. In some sense, it's because plus k and minus k balance one another always in a Majorana system. So there is no Fermi surface sum rule in this particular case.
You also have particle Hall symmetry.
You have a particle Hall symmetry, but that means that in some sense, one half of the Brunzone is compensated by the other half of the Brunzone. So one is a particle, the other one's holes. And in fact, you can even, so this is an example of Hermansen Krebs from 3 dimensions. This is not, however, a gapless spin liquid, because in this system, if you flip a spin, you also interfere with the bonds, and you flip a bond, and this creates 2 vortices either side of that bond. And so this family of spin liquids is actually a gap spin liquid, which means that if you tickle them, if you couple them up to some surroundings, they're robust initially, they've got a gap. Okay. However, you can take this model and modify it by introducing, as I'll discuss later, orbital degrees of freedom. And you can actually produce a 3D Majorana Fermi surface of gapless excitations. And we'll come back to that later in terms of a modification of the Kitaev spin liquid called a Yau-Li spin liquid. And an exercise, you could even take these models and go to higher dimensions. This trick of constructing lattices can be pushed to at least to 4 dimensions. And with a student recently, we managed to show that this 4-dimensional lattice, that's a projection of what it looks like into 3D, actually has an exact Kitaev solution and a Yau-Li solution, although it doesn't actually have a Fermi surface.
Yes.
Yeah.
There's a question.
Yes.
Can I just want
Yeah,
to try to understand,
yeah.
so you're, okay, the 3D one has a sort of Majorana Fermi surface.
Yes.
So your definition of a gapped versus gapless spin liquid is whether the microscopic, like spin.
Yeah, so in this particular case, if I take the sigma and I act on the ground state, I create a gapped excitation, right? But it turns out that you can decorate this sigma I dot sigma j with an additional term, a Heisenberg coupling term. And that if you regard those as the spins, okay, they inherit the Fermi surface, but now become a gapless Fermi surface of spin excitations.
But okay, and just about this model though,
Yeah.
like when you say it's not gapless, you don't mean there's no physical degrees of freedom that will see this Fermi surface. It's a statement about.
That's right. So it would have a linear specific heat, for example, right? It would conduct heat, but the spin correlation function would have a gap, in it.
Right, but still, there's from the surface, there is gapless excitation.
There are gapless excitations. They just don't carry any spin.
Right.
You're saying it's got a spin gap.
It's a spin gap. That's right. Yes. Okay. Now, these models, if you integrate out the fermions, describe the discrete degrees of freedom on the bonds, form a so-called Z2 lattice gauge theory. And the underlying physics of it is literally a model in which the cost of flipping a single bond has a plaquette cost. And so this is a simple model of the underlying static physics of this class of Kitaev spin liquids. And these models were studied by Franz Wegener back in the 1970s as examples, simple examples of gauge theories. Literally, you have a bond which could be plus or minus, and the cost of if all the bonds around a loop product up to +1, that's the lowest energy configuration. And this class of theory actually has 2 phases. It has a deconfined and a confined phase. The confined phase being the one in which the vortices disappear. And so the gauge field is now no longer active. And that's what makes, it's that confinement that makes the physics on the left-hand side so interesting, because once we remove the fluctuations, the thermal fluctuations of gauge fields, the residual Majorana fermions propagate coherently a lot throughout the lattice. Yeah, there's 2 questions here.
Just small comment. So +1 for this plaquette operator only in some system. It depends on the size of the loop. So depending on the different
Yes.
loops in this 3-dimensional construction, it
Right.
could be either +1 or -1.
Could be, yes, that's right. And so these particular models here have the case where it likes to have a +1. Yeah, that's right. This is connected with Leib's theorem and all sorts of other things, yes.
So just from my understanding, like how is your vortex defined?
The vortex would be a loop in which the product over the uij's around the loop are equal to +1. Okay. So in the case of the honeycomb lattice, it's easy. It's just a plaquette of six bonds. It's a honeycomb plaquette. In this lattice here, you have to trace out actually 8 sides before you come back to the same point. Okay, and so it would be that loop. Interestingly enough, this model here, you might wonder how we actually know that it costs energy to make a plaquette. Well, we've actually calculated the energy to flip a given bond. At least we know locally it's the lowest energy state. So actually in 3 dimensions, such lattice gauge theories have a phase transition as a function of temperature. And so in this 3D so-called hyper-octagonal lattice, as you cool it down, there is in fact a phase transition into this confined phase at a particular value of kappa particular value of temperature. And so there is actually a curious phase transition without any order parameter. It's an Ising phase transition without any order parameter in which the spins break up as you go to lower temperatures into these fractionalized degrees of freedom.
Is there a measurable anomaly at TC?
Yes, specific heat capacity. Right, that's what you see. But it would be one of those things where you, if you tried to hunt for the order parameter, you'd never find it.
And you call it topological order.
It's called topological because the ground states that are formed are sensitive to the manifold on which you put the lattice. So they have a degeneracy which senses the connectivity of the edges. So that's the topology. And it's not my terminology, it's others' terminology. Okay. Yeah. Okay. So how is this interesting? Well, because we can use these ground states and we can ask what happens if we couple them up to charge. What we'd really love to do is to dope them. We don't know how to dope them, but we do know how to connect them up with conduction electrons by an exchange interaction. And interesting physics takes place. But why would we want to even do such a thing? Well, it keeps us off the streets, but actually there are also materials which really challenge us at the moment and suggest there may be novel types of fractionalization going on. And I just give you some of my favorite examples. This is samarium hexaboride, which is a topological insulator at first blush. Okay, but it has the bizarre property that it has a linear specific heat in its insulating state, and we don't know what produces that insulating specific heat. And furthermore, some experimentalists have seen de Haasman-Alfvén oscillations in the magnetization, and these de Haasman-Alfvén oscillations can be traced out to give a Fermi surface, which is characteristic of the underlying. Well, it looks as if there are unhybridized d electrons in the system. Okay? And these data have been confirmed independently by the group of Art Ramirez, first discovered in Cambridge. But our group of Art Ramirez very carefully measured the specific heat capacity of this system, and they've also seen quantum oscillations in the specific heat. Some people have said, well, how do you know you don't have traces of aluminum in your sample? After all, you made this out of an aluminum flux, aluminum flux. Well, actually, these data have been made using image furnaces, and there is actually no flux involved in making the sample. And still, you see these oscillations. So this remains an unsolved paradox of this particular material. Okay, and it's led to the notion: well, could you have a neutral Fermi surface? And even such a statement is a little bit of a contradiction. How can you have a Fermi surface that gives de Haasman-Alfvén oscillations, gives something resembling cyclical motion if it's neutral? Doesn't make sense, right? Okay. And so we've been interested in this because this is the picture of a conventional Kondo insulator. It's a picture in which you have local moments interacting with the conduction sea, forming singlets, and those singlets create a nice gap, and you get a superconducting forming, even though you have a half-filled band of conduction electrons. This is the simple picture. And we can understand this picture using the Kondo lattice picture, in which the spin fractionalizes as Dirac electrons. Okay, and these Dirac electrons can then be thought of as hybridizing with conduction electrons. And this macroscopically entangled state is then an insulator. This is the basis of the understanding of the Kondo lattice of heavy fermions. If you can form an insulator, you can then dope it a little bit, and then you'll get a heavy Fermi surface. Okay? And there's a whole basis of understanding for this. But one of the things you'll notice is that in order to make a spin into a fermion, you have to expand the Hilbert space, which means that you're really thinking naively as if the F electrons have a Hilbert space where they can be empty, singly and doubly occupied. Okay? Yet the physical Hilbert space has a spin there. The spin is only a two-dimensional Hilbert space, but it's pretending it lives in a higher dimensional Hilbert space. And the only way this can be the case is if there is a emergent gauge field, in this case an emergent U1 gauge field, which keeps track of the Hilbert space. It seems like a rather fantastical description, but it seems to work, and it can be made consistent with something known as Ishikawa's theorem, which says that if there's a Fermi liquid, then that very liquid will count not only the number of electrons, but also the number of spins. Okay, so we understand this very well, but that doesn't explain this physics. And it raises the question, could there be new kinds of three-dimensional spin fractionalization, not only ones that involve the spin liquid, but also ones which perhaps engage and connect up with electrons? If a spin were to fractionalize in a new way, and then were to hybridize with electrons, what kind of state would you form, and how would you know if you've had it? That's the question raised by this.
Can you clarify why 3D specifically? Why not even?
Well, particularly because I'm interested in materials which are not two-dimensional, that really are three-dimensional. So anything that's particular, the 2D, would not explain their physics. Okay, so I don't want to take advantage of braiding and things like that, which are very particular to two dimensions. That's why I put the word 3D. And this system is manifestly cubic. So if such an idea were to work, it would have to be three-dimensional. Okay. There are other, and so one thing that we've been interested in for a long time is the possibility that the spin would fractionalize in a different way. And one way to write down the spin operator is as a product of Majorana fermions. We've been playing with this, not knowing how to do any controlled treatment of the model for years. And we know that if such a fractionalization were to take place, then now the spins would now be represented not by a four-dimensional Hilbert space, but by a 2√2 dimensional Hilbert space. Because we have three Majorana fermions here. Those three Majorana fermions now, if they were to hybridize with conduction electrons, would no longer, would there be a mismatch. And so if you think of a conduction electron spin up and spin down as two Dirac fermions, which then breaks up into four Majorana fermions, four cannot pair up with three, and you get one leftover band. And it's the possibility that such a leftover band might have some connection with this curious neutral Fermi surface that has attracted us for a long time without actually solving the problem. And so such a fractionalization, it's not clear what state you actually have here, because in order to choose one out of the four Majorana components, you have to break gauge symmetry. And so it's not immediately clear whether such a state would be an insulator or whether it would actually be an exotic kind of superconductor. Yes.
Yes, this approach is basically, let's assume that it's fertilization is like this. Let's see consequences.
Let's throw it in, yes.
Yeah. If I start with different one, if I say there is a Hamiltonian, there is interacting Hamiltonian.
Yes.
Is it known where to look to search for this kind of fertilization?
Well, the problem is the following. You can make such an ansatz, and there's typically, and you can then say, well, I believe my mean field theory, and then you will stand up and say, but Piers, have you examined the fluctuations around your mean field theory? And I would say, well, unfortunately, I can look at them, but I have no guarantee that they are not so large that I lose my saddle point altogether.
Right, but I'm asking slightly different
Yes.
question. If you don't know which fertilization is right, and you want to start with some microscopic Hamiltonian,
Yes,
and you want to see what kind of fertilization emerges in the system
Yes.
as some sort of instability,
yes.
is it known how to search for this?
No, not really. It's a kind of ab initio thing where you put in the thing you're looking for, and then you say, well, okay, these are two different ways of fractionalizing, which one wins?
Yes,
Okay, right? And you wouldn't have an honest way of answering it.
Mhm.
Okay, right?
Before you move on,
Yes.
a couple of questions.
Yes.
So you mentioned the Husband Alphen and specific heat measurements, one oscillators.
Yes.
So these sets of data are fully consistent.
They're mutually consistent.
For Samir, spherical, right?
That's correct.
You list two other systems out there. What's
Yeah,
what's
so both of these systems look like they're topological in the sense that they have conducting surface states, they're good insulators. And in each of the cases, there are examples of quantum oscillations that look like bulk quantum oscillations. And so what's producing that? This is the enigma paradox posed by these materials. Okay, let me just go on and look at my other motivation, which is this crazy guy. This is uranium ditelluride, which is a strange superconductor. At first sight, it looks like a perfectly average heavy fermion superconductor. It's got F electrons on the uranium sites, and it goes superconducting. In the early samples, it went superconducting at 1.5 Kelvin, and then they discovered a nice way of making this in molten salt, and the TC went up to 2 Kelvin. So what's remarkable about this system? Well, it's been called a Lazarus superconductor because it has an upper critical field that swims with the big guys. It's a heavyweight a heavyweight system in a field, but it's a featherweight system in temperature. So this is the phase diagram compared with the cuprates, the iron-based systems. Its TC is basically 0 compared to these systems, but its upper critical field is known to, in one particular set of directions, to exceed 80 Tesla. How can a 2 Kelvin superconductor have an 80 Kelvin upper critical field? This is a fascinating question in an era where we're trying to produce high field magnets. If we could understand this, maybe we could make new kinds of high field magnets. Okay. And this is the phase diagram of this system. This is no longer just an archive. It's been the group that's been working on this is very good at coming up with great names, and so they call this the halo phase. And the reason it's called the halo phase is that around the p-axis, you can actually follow the superconductor all the way around. This is a re-entrant superconductor. In this system, it already has a very large upper critical field for its TC. You can see that this is the upper critical field hovering between 10 and 20 Tesla in these different directions. But along the p-axis, there is this column of superconductivity that extends up to a first order phase transition where the spins finally lock together in a parallel configuration as a first order metamagnetic transition. But if you would go out at a certain angle from the p-axis, then superconductivity re-emerges and extends on up to 60 Tesla in this direction. But in this other direction, which involves the BA plate, the BC plate, no one's actually seen it go all the way up here, but they can extrapolate, and they can already extrapolate well above 70 Tesla. It's believed this thing probably goes up to 80 Tesla in these directions. In all of these directions, you've got major questions. For example, okay, this is obviously not orbitally limited. It's obviously not power limited. It's orbitally limited. But at 80 Tesla, you have to have extremely short coherence length. That's such a high upper critical field. How can you have such a short coherence length with a 2 Kelvin superconductor? This is a system which, if you look at the numbers, simply would have a coherence length comparable with a cuprate superconductor, even though it has a TC of about 2 Kelvin. Yes.
Yeah, is there a situation for particular field direction? When you start with 0 field, you apply a field up to 80 Tesla, and superconductivity never disappears.
No.
Or, but
There is
that's how we mean this upper critical field. It looks to me that this is superconductivity confined to.
However, if you put pressure on it, you can actually distort this high field phase to lower pressures, and it seems to connect up with the low field phases. So in that sense, if you're willing to go out in the pressure direction, you can get up there.
And people did this, or
They have never done that. They have connected up the different directions. They've never put pressure on it, increase the field, and release the pressure. That would be an impossible experiment, I think. Yeah.
Probably a bit lost, but how this is connected to fractionalization?
Well, because this, I'll come back to that in a moment, but at first sight, it seems to be something that's very difficult to explain within our current understanding of triplet superconductors. It seems to be so outside the. There is one other aspect which I'm going to come to, which is the apparent presence of broken time reversal symmetry in the system, which really does raise eyebrows, and it's a little bit controversial, but let me come to that right away. So in this particular system, there are some indications of broken time reversal symmetry. And one of the indications is that actually, if you look at STM measurements of this system, you can actually find evidence that there's indirect evidence for the presence of a chiral edge state. And this chiral edge state is seen through the kind of Doppler shift in di by dv, and the authors of this particular paper interpreted this in terms of the linear combination of two different representations of pairing. Pairing 1 plus I times pairing 2, which then produces a topological estate. But such a topological estate poses headaches for us in terms of our understanding. Number one, in this orthorhombic crystal, there are no two-dimensional Cooper pair representations. Furthermore, there are no three-dimensional broken time reverse symmetry topological superconductors in a tenfold way. So that if these statements are correct, it's very difficult to accommodate them within a conventional picture of BCS pairing. So this is by way of motivation. It's not by way, if someone comes up with a very nice explanation in a conservative framework, I'll be the first to embrace it and say, that's fine, it's okay, we understand it now. But at the moment, it seems to suggest that we need to think outside the box if we're to understand this material. Yeah.
So the material is three-dimensional?
Yes.
Okay, but and then they're doing STM on like a top surface.
Unfortunately, there's only one surface that actually cleaves.
Okay,
And
and then their claim is that maybe on that surface you see something.
yes, and there are counterclaims to this, as you can imagine, in any experimental work, there are other different points of view. Yes.
But so if you're seeing a correlation on the boundary would at least be on the higher order ones? Like it would be-
Well, no, well, it's on a surface. These things are going on. These things. The interpretation is that there is actually a current running along the surface, okay, and that you can see it at these step edges. It may be, as you say, that's not the right interpretation, that there might be something exotic running along the step edges, and then it would be a higher order topology. Okay, that could be another interpretation.
Is this experiments at zero field or is it
These are experiments at zero field, yes.
And is there any evidence that time reverse symmetry is broken in the superconducting state? But
Well,
not the temperature,
let me tell
not
you
the
this.
temperature above.
So, like all time reversal symmetry claims, there is a history of disagreement. So the first experiments were done by Aaron Kapitulik, and he saw his Kerr rotation. And then later on, his grand student, meaning a student of a student, did a similar experiment and found no evidence for Kerr rotation in better samples. And that's where we lie at this point. Okay, but the original lab has never gone back and repeated the experiment to check, oh yes, you're right, the better samples, it's disappeared now. Okay, and so we don't know is the answer to that question. So this motivates the consideration of alternative classes of order parameter. Is it possible to have new classes of order parameter if we think about what happens when fractionalization interplays with superconductivity? That's the question this raises. Okay. Okay, so now coming back to this thread of Kitaev and bringing electrons together with the Kitaev model, let me tell you about what we've been doing. We've been playing with this hyper-octagonal model, and we've been doing things to it which enable us to actually look at the interplay of the spin liquid with electrons. And so this is the model, the CPT model. It involves conduction electrons running around this curious chiral structure. It involves the spin liquid, and it involves a Kondo coupling that connects the three together. Okay, let me just show you what that Hamiltonian is. So first of all, this is the Yau-Li model, generalized to this three-dimensional hyper-octagonal lattice. You can see it contains not only an orbital degree of freedom with an XX, YY, ZZ coupling, but also a Heisenberg spin coupling. This peculiar combination is exactly solvable, and what happens is that the Majorana fermions from these orbital degrees of freedom get absorbed by the spins and convert the spins from bosons to fermions. And these vector fermions then buzz around on this Fermi surface. It's exactly solvable, and it's an amusing curiosity. And this is how the spins fractionalize on this Fermi surface. They fractionalize in our favorite way. They fractionalize as a product of Majorana fermi. So as you cool this spin liquid down below a certain temperature, the gauge fields freeze out, you get this topological phase transition, and these Majorana fermions start running around on this lattice. It's a free Fermi theory of Majorana fermions at low temperatures. That's what it is. And so we became interested, could we couple it to a conduction sea? Could we now put a conduction electrons on this very same lattice, have them hop around, and couple them with a Kondo coupling to the local moments? Can we now use this construct to examine what would happen if we did such a thing? Okay.
So, sorry,
Yes.
sigma in the bottom line, the S in the bottom line is that?
Yeah, bad notation. Sorry. What this should have said is S. I should have had an SI.SJ here, and this is then SI dotted into the spin density of the conduction sea. Okay, sorry, it's bad
So
notation.
sigma is capital S.
Sigma is capital S. That's
Sigma
right.
in the second line is capital S.
Yeah.
it's the
Yes,
bottom line.
Yeah, sorry, my apologies.
Yeah, sure.
Okay, right. So, and what we discover, and I'll show you some of the details of this in a moment, is that because the two Fermi surfaces are completely matched up, they have a kind of, they are in the same classification of models such as the Piles instability or the BCS instability. It turns out that there is actually a logarithmic instability in the system in which the electrons here love to bind to the Majorana fermions that are here. And when they bind together, they produce a new state which actually has a charge E condensate. And so the question then raises, well, what the hell does that mean? And how can we understand it? So at the level of doing the calculations, let me run you through some of the details, a deeper dive into the theory. Okay. So first of all, this is the Yaoli model that we've seen before. And at each site, there's a spin and an orbital degree of freedom. Okay. This is the Yaoli model. And what happens here is that the orbital degrees of freedom in blue and the spin degrees freedom in red have different roles. Okay. So first of all, the orbital degrees of freedom, they gap out and they give rise to the Majorana fractionalized spin liquid. And how does this happen? Well, the orbital degrees of freedom provide the bond variables as they do in the characteristic Kitaev model. And they then liberate a Majorana fermion that's absorbed by the spin degrees of freedom, and fractionalizing them into spin 1 Majorana fermions. Okay. So that's what happens with the Yaoli model. And at low energies, the Yaoli model can then be described as a gauge field in which the gauge field provided by the orbital degrees of freedom governs the motion of these Majorana fermions, but which now carry spin. And what's important about this is that when we flip a spin in this system, since the spin operator is gauge invariant, it doesn't actually create any gauge field perturbations. And so you can flip a spin without affecting the gauge fields, and therefore this is a gapless spin liquid. So that's the Yaoli model. And so now the next thing we're going to do is, and this is the Bison connected with that Yaoli model. It's a very exotic thing that governs all these sites here. If the product of the extremal spins around this Bison is actually a constant of motion, and that's what drives this gauge physics. Okay.
But just, is this like the Kitaev model, you just need to try?
It's just like a Kitaev model, and the only difference is that it has spinful Majorana fermions running around rather than spinless. And we're basically borrowing the method that was developed by Yao and Dunhai Li, and we're putting it on a three-dimensional lattice. Okay. So, and this is the band theory of that thing, and this is the Fermi surface it gives rise to. Okay, so much for that. The question is, what can you use this for? And so now what we're going to do is we're now going to couple these spin degrees of freedom to electrons. And so here is the spin degree of freedom sitting here that's fractionalized, and we're going to couple it up to this electrons buzzing around on the very same lattice. And provided we do this at exactly half filling, they have Fermi surfaces that perfectly match up. Okay. And the other important thing is that the fractionalization guarantees that this spin, when I flip a spin, creates a pair of fermions. Okay. And unlike other approaches, such as the Dirac fractionalization of a spin, all of the constraints are completely taken care of in this procedure. There are no horrible fluctuating gauge fields that we have to control here. They've all been taken care of by the phase transition that, that confines the Z2 degree of freedom. And so now we can proceed with this formulation of the Kondo effect with old-fashioned many-body physics. This fractionalization has taken place, and now we need to think about this interaction here, okay? And so you can rewrite that with a little bit of manipulation in this suggestive fashion as the square of two spinors, okay? This is basically spinor, dagger, spinor here, where this spinor here is the combination of the Majorana fermion dotted with a Pauli matrix and a conduction electron. So this is a bound state. It's a spin 1/2 boson. It carries charge E. It carries spin 1/2. It also carries the gauge charge of the chi fermion, and we would normally not think about taking it seriously, excepting for the fact that we know that in the ground state that the Z2 degrees of freedom are constants of motion. They're factored out, and so we can do old-fashioned many-body physics on this. Okay. And so once we've got it in this form, we're invited now to factorize the Hamiltonian in this particular fashion. This is an electron coming along and becoming a Majorana fermion and spitting out a condensate, a charge E object. Okay, and so at the mean field level, this is a reasonable thing to do. And moreover, here's the thing about this model. Here's the model. So here's the model in its fractionalized form. Okay, and so the important point here is that these two Fermi surfaces nest up with each other. And so we have an electron Fermi surface degenerate with a neutral Fermi surface. And if we look at the susceptibility, the 1e susceptibility, it has a natural logarithmic pole in it. And so we can do old-fashioned many-body physics, and we can allow this B to condense, and we have a logarithmic instability. So it means that for an arbitrarily small j, this instability will take place. Okay, an infinitesimal coupling of the conduction C to the spin liquid then forces this thing to condense into what looks ostensibly as a charge E condensate.
And the sign of coupling is such that you do get the stability.
That's right. If I change J and make J ferromagnetic, I won't get an instability. So it really is a Kondo effect, but taking place in a lattice with fractionalized spins. And so at this level, this is seems to be a reasonable thing to do. We have this temperature, this Ising phase transition at which the gauge fields disappear. And below that, we have a Cooper instability, excepting it's an instability between an electron and a neutral fermion. It creates a charge E condensate. So what is this thing? And what does this tell us? Are we being deceived by our calculations? Or should we think of this as something that might somehow occur in a real system? And is it a proof of principle of a different kind of superconductivity? Those are the questions it raises. Okay. And so we can only understand this as very small j, but we can also go to very, very large j in this phase diagram. And so all the way out here, very
So
large.
very small G effectively means at zero temperature.
At zero temperature, that's right. Okay. But what we can do, so we can understand the model here, okay? And everywhere else is really terra incognita, except J very, very large. And when J is very, very large, what happens is that the Kondo effect completely takes over. It grabs that spin and forms the Kondo insulator, okay? Which is this phase here with some kind of crossover at Kondo temperature, but that then leaves behind these orbital degrees of freedom, which have a residual interaction through the Kondo insulator. And so what happens in this region here is that we have the coexistence of an orbital spin liquid with a heavy fermion state of matter. Okay. If we dope away from half filling, this transition here now moves out to a finite coupling constant. Okay. And in between here, we've basically done our best to do some calculations that suggest the form of the phase diagram. It's rather speculative, but we believe from calculating the Bison energies that TC1 comes down. We can't prove it, but we think that in order to connect up these two phases together, we most likely have a quantum phase transition between the two states. One which goes from this putative 1e superconductor to this orbital spin liquid. And it's this phase boundary here that fascinates us the most, because if this phase boundary were to exist, it would mean that we could go from a heavy fermion state of matter into this exotic superconductor. We wouldn't have to first form the spin liquid before we went there. It would provide an extra route. And the question would then be, well, what would be the nature of this phase boundary here? Okay, and these are all completely open questions. We can solve this problem down here, and we can solve it up there.
What happens if I start with smaller values of J and go down? I go through a Fermi liquidation, but then I go back to the same phase. No, not here, not here.
Here.
Even further.
Here.
Here. And I go down, vertically down.
Right, so if you go down here, what happens is that I have this phase transition in which the spin-ons bind to the electron.
But it's the same phase.
It's the same phase.
Right. So I mean,
So the orange phase is the same on both sides, right? But we don't know anything about this second phase boundary here, right? But it looks to us as if there's the potential for a phase transition from a conventional Fermi liquid into this exotic superconductor. Going this way.
okay, and if you go vertically at smaller J, then you do the same, no?
If you go vertically through
Down
here,
yes.
now what happens is you go through this what we call an Echo star with a small Fermi surface, conduction C, coexisting with a spin liquid. And then what happens is that this instability develops when we go into this orange phase here too. Okay. So we've been trying to play with this model in various contexts. We're looking at one-dimensional versions of it. We've also played a few interesting things. One of the things you can do is you can add spin-orbit coupling. We did this because we were interested in the topology. We can only do that. We're only doing that in 2 dimensions. And if we add spin-orbit coupling to the 1D to the 2D model, we do indeed produce a broken time reversible symmetry topological superconductor.
So I think it's spin-orbit coupling you for conduction.
So in the conduction atoms, that's right. Yeah, and also that's right in the conduction atoms. We've also looked at the effects of doping system away from half filling, and something interesting happens there. We actually get a pair density wave. In fact, the ground state that we form even at half filling is a kind of full de Ferrel superconductor because of the mismatch in locations of the Fermi surfaces. But the moment we dope it, in fact, it develops a kind of Larkinov-Chinnikov phase in which the magnitude of the order parameter starts to modulate. And so this provides actually one of the first examples of a model which naturally produces a pair density wave within the mechanism. Okay, so to go beyond that, we've been puzzling, and one of the questions is
So
that
I'm not sure that I understand about the doping. So you
Yes.
have already the fermionic electronic system and you have the spin system. So you
right,
have
so
to just
all of this was done at half filling, where the 2 Fermi surfaces completely match.
and now you dope.
Now I dope one, which means that the electrons acquire there's an electron on a whole Fermi surface, and this one gets smaller, one gets larger, but the spin liquid is unaffected. And so now, in order to hybridize, it prefers to shift over in momentum space and produce an incommensurate superconductor.
But particle Hall symmetry should be still preserved.
Part of the one Fermi is not of the conduction electron.
Yeah.
But once you hybridize them through the Kondo coupling, you have some new quasi-particles.
You do, and one of the interesting features of this superconductor is it actually has a Fermi surface of neutral excitation in this simple form. Yes,
Here's a simple question. Standard FFO state
yes,
appears at a finite field because you need to overcome stiffness of a superconductor.
right.
Why here it appears instantly?
Well, it doesn't appear instantly because, first of all, this instability at J equals 0 moves to a finite J
Okay.
the moment I dope the system.
Mhm.
And furthermore, yes, you're quite right. In fact, I still need to go there is a threshold, I'm forgetting the phase diagram right now, so I can't quite answer that question.
Okay, go
But we did think about this.
And on the
We are coming,
Yes,
to time.
couple of minutes.
Okay, so I'm basically done. I just wanted to mention that we've been looking at a model which has some elements of this physics, just for interest. This is the XY model, which is gauged. And it's interesting because the order parameter here has a Z2 charge. And so you can ask the question in a not a quantum, in a classical model, what can happen to this model at fine temperatures in 3 dimensions? And this is a model that's been actually studied over the years by many people, but it became possible with Anatoly Kuklov's genius to actually study this in very, very large system sizes. And we found some rather interesting physics. So this problem has bosons, and these boson loops can actually be modeled using his worm algorithm. And so this is the phase diagram of this model. It has on this axis here just the confinement of the bosons. And on this axis here, it has the formation of a psi squared condensate of the pairs of these psi degrees of freedom up here. And we were interested to look at what might happen in this region here. We know that psi squared is finite, but what happens to psi itself? Okay. What does its correlation function look like? And we're also interested in the physics of the interplay of here is a pi vortex of the psi field, which can actually bind to a boson, and these two guys can come together and form confined objects. And does this allow the psi field to exist in this region here? So anyway, we did a large-scale simulation of this, and we were able to look at the gauge invariant correlation functions of the psi's. And we found that typically the correlation lengths were huge. They could become as large as 50 or 75 sites. Here, these are the radius of gyrations. R2 is the radius of gyration of psi squared, and R1 is the radius of gyration of psi with the gauge field connected here. And you can see that here the radius of gyration has gone all the way out to 20 sites, at j equals 1.5. And so what happens in this is that though this psi quark is confined in the ordered phase, the size of the meson is huge, which would mean that the interior of the bound state of these two confined quarks would actually be very, very large. And we're also interested in looking at this model with an electromagnetic field, and we can kind of argue that we may actually get H over E vortices when we put in the electromagnetic field. Anyway, so just to end the physics, strange superconductors and insulators raise the possibility of novel forms of spin fractionalization, and these could influence the kinds of order that we can get. I've shown you that this 3D Yardley spin liquid, when we combine it with a Kondo lattice to make this CPT model, we can see that there's a new kind of superconductor that emerges. Topological superconductivity is present in this model, at least in 2 dimensions. And I've just very quickly shown you some worm algorithm studies of the Z2XY model that show that the charge E order parameter has a huge coherence length in the psi squared ordered phase. That's it. Thank you.
Any questions during the talk? More questions? Yeah.
One quick question. In the CPT model, you said that these were in the confined phase.
So
What happens if you have a deconfined phase for the?
So these words, yeah. So the gauge fields are confined.
Yes.
Of course, when the superconductivity takes place, it becomes more complicated because what's happening here is what the particle physicists would call a Higgs phase is developing. And so then the question then arises, are you still talking about a confined phase of the C2 degrees of freedom? In the case of our model, because it's a Kitaev model at 0 temperature, there are no fluctuations of the gauge field, so we can be quite confident about that. But at fine temperatures, it starts to become ambiguous, which is why we started thinking about this simple case of the world algorithm, presumably at finite temperatures, it is actually technically a confined phase because the C2 charge will now be affected by thermal fluctuations in the same way that we saw in world algorithm. However, although it's confined, we think there must be very, very long coherence lengths. We don't know what would happen if we added in the electromagnetic field, which would change the discussion, and it may not really matter, because if the mean field theory gives you a pretty good description of the problem, it may be that indeed those quark order parameters are confined, but nevertheless, the phases they give rise to, for example, the possibility of broken time reversal symmetry, give you a wider class of classifications of phases than would be possible with a conventional VCS superconductor. Yes. Alex.
Your, as far as I understand, your Hilbert space is a direct product of spin space where you have your S operator.
Yes.
And Fermi.
Yes.
Can you write a BCS quote unquote and ground state wave function?
No, because yes, we could if you don't mind that VCS wave function involving also the spin-offs.
Of course.
Okay.
But spins.
Well, so those things are then the fractionalized spins, and if you wanted to formally write down the wave function, you'd have to include a projection to write the thing in terms of the original Hilbert space.
Yeah.
Okay. So yes, one can do that. But it wouldn't be very satisfying to you, because it wouldn't be in the terms of the original degrees of freedom.
Yes, but if I can.
Yeah.
But still, the question is, if you can do this.
Yes.
The question is, we know that number of universal ratios in BCS. In your case, suppose that you explain superconductivity with spin fractalization. Can you predict some new universal ratios like jump of specific heat or 2 delta over TC, something like this?
Yes, for the small j, one could do that. Yeah.
It'd be interesting to see
Yeah.
what comes out.
Not that we know of any material which is a good candidate for that. Yeah, so it would presumably have some universality. To what extent that would be dependent on our crazy lattice, and to what extent it might exist separately from that, another question.
More questions? If not, that, well, thanks very much.
It doesn't answer the 90 questions, but they don't seem to have spoken up, so.
No problem. You do now, but then let's. Yeah, so. Really needs to. That must be.